Welcome, curious minds, to another deep dive. Today, we're not just sifting through data, we're taking a thrilling plunge into arguably the most complex and fascinating data source of all,
Right.
the human brain.
That's right.
Our mission, to explore how we can take those raw, kind of squiggly brain signals and transform them into incredibly insightful and, honestly, surprisingly beautiful visual maps.
Exactly. We're embarking on a journey today to unpack the whole process of transforming raw electroencephalography, that's EEG data.
Right, EEG.
You know, those tiny electrical whispers from your brain. We'll walk you through the real-world challenges, the surprising detours, even some clever coding puzzles we had to solve, and ultimately create a dynamic animation that shows your brain's electrical activity quite literally dancing across the screen. It's really like seeing your thoughts in motion.
Wow. Imagine for a moment being able to literally see the electrical echoes of your thoughts sort of rippling and shifting across your scalp.
Yeah.
That's the ultimate payoff we're building towards today. And, well, trust me, it sounds like a wild ride.
It can be.
So let's kick things off right at the beginning. We've got this raw EEG data, but it's certainly not a ready-made masterpiece just waiting to be admired, is it?
Not at all. No.
Before you even dream of seeing those beautiful brain maps, what are the very first, foundational hurdles you hit when trying to transform that raw signal into something meaningful, like a top map, that colorful map of activity across the scalp?
Right, the top app.
It sounds like there's a lot of groundwork needed first.
You've hit on it perfectly. There's a definite and often challenging journey from those raw, kind of noisy signals to a coherent, interpretable image.
Okay.
For this deep dive, we faced 3 core technical hurdles right out of the gate, and honestly, they're common tripwires in this field.
Oh.
Think of them as the foundational building blocks you have to get absolutely right, otherwise your whole visualization just won't make sense, you know?
Makes sense. So what's the first one?
The first was ensuring that the specific electrode names in our dataset, like the ones labeled in RAWs 0402.chic names, perfectly aligned with a standard electrode map, like the standard 1005 montage.
Okay, so alignment. Why is that so critical?
Well, it isn't just about pretty names. It's like trying to assemble a puzzle where half your pieces are labeled for a different puzzle box entirely. If the system doesn't know exactly where each electrical signal is coming from on the scalp, your map will be skewed, or worse, just plain wrong.
Right. Garbage in, garbage out.
Precisely. We ended up having to implement a clever mapping technique, often using something like a Python dictionary, to meticulously clean up and rename our channels. We used a method called strip, just to clean up some trailing periods.
Oh, little details like that.
Exactly. To achieve this crucial alignment, it's the data cleaning step that truly makes or breaks your analysis later on.
Okay, so channel names, get them right. What was hurdle number 2?
Second was accurately calculating the Power Spectral Density, or PSD, for the brainwave bands we were interested in.
PSD, okay, Power Spectral Density. Break that down a bit.
Sure, it sounds a bit technical, but think of it like tuning a radio to isolate a specific frequency.
Okay.
Imagine you want to isolate just the alpha waves, which are usually found between, say, 8 and 12 hertz.
Right. Alpha waves often linked to relaxation.
Exactly, that relaxed but awake state, like when you're just chilling out with your eyes closed. This involved precisely defining our time windows and frequency ranges. We used the Welch method, which is pretty standard for this calculation. Getting this right is absolutely vital for isolating the specific brain activity we actually want to visualize without all the noise from other brain rhythms interfering.
So you're filtering out the noise to see the signal you care about. Makes sense. And the third hurdle.
And the third hurdle was getting the top map plotting function itself to correctly map that isolated brain activity onto a scalp diagram.
Ah, the actual plotting.
Yeah. This required precise channel location information, which, again, comes from that standard 1005 montage we just talked about. If the names are right, the locations should be right.
Right, it all connects.
And a neat trick we actually used here was creating a mock evoked array object.
A mock object, what's that?
Well, in the MNE-Python library, which is a popular tool for this,
Okay.
evoked objects typically represent the brain's average response to a specific event or stimulus, like a flash of light.
Okay.
By simulating this structure for our continuous data, we could cleverly leverage MNE's powerful built-in plotting functions, even though our data wasn't strictly an evoked object in the traditional sense.
Ah, so you tricked the tool into working for you. Clever.
Kind of. It's like giving a specialized tool a slightly different but compatible input so it can still do its amazing work.
Okay, let me try and summarize. It really sounds like trying to teach two different dialects of the same language to understand each other, or making sure all your puzzle pieces are genuinely from the same box, as you said.
That's a great analogy. Yeah.
Because if the coordinates are off or the names don't match, your map is just meaningless colors.
Pretty much.
When you first started digging into this specific data set, did you run into any immediate roadblocks? Like, what was the first sign you actually had a problem?
Oh, absolutely. The very first hint that our puzzle pieces weren't quite fitting came as a value error. Python loves throwing those.
Doesn't it just?
And it loudly proclaimed, the following electrodes have overlapping positions.
Okay.
That message was our clear signal that, despite our careful planning, we still had some deep-seated mismatch issues to sort out with the channel locations, probably stemming from those initial naming discrepancies we talked about.
Right.
It was the moment we knew we needed to put on our serious detective hats.
That error message sounds like the universe telling you, hold up, go back to the drawing board. How did you pinpoint the exact mismatch? Was it like pulling a thread or more like, I don't know, forensic analysis?
It definitely felt more like forensic analysis. This is where the detective work got truly fascinating and, gotta admit, a little frustrating too.
Yeah.
We literally had to compare the channel names from our specific data file, the WFDB-CAL file for this deep dive, against that comprehensive standard 1005 montage.
Okay.
Now, our data set had 64 channels. The standard montage lists a whopping 343 channels.
Wow, 343, that's a big difference.
Huge. It's like trying to find specific addresses in a small village using a map of an entire continent.
Okay, yeah, good luck with that.
Exactly. And what we found was a genuinely surprising fact. Only 36 channels are common to both lists.
Wait, only 36 out of 64.
Only 36. Think about that. Less than half of our dataset's channels actually mapped directly to the standard.
No.
We quickly identified the misfits 28 channels in our dataset that simply weren't in the standard montage. They often had very specific prefixes like A, CP, FC, FTPO, and TP.
Ah, so different naming conventions entirely.
Seemed like it. It was a real aha moment, but also a kind of uh-oh moment because the top map did eventually plot, which was a good sign.
Okay.
But it was based on the severely limited subset of just 36 channels.
Right. So what does this all mean for you, our listener? Whether you're trying to interpret these brain maps yourself or just understand the journey of dealing with complex data.
Yeah, this is crucial.
It's like trying to, I don't know, diagnose a complex electrical fault in a house by only checking like 10% of the wires.
That's a good way to put it.
You might get some information, but you're missing a huge portion of the picture.
Absolutely.
This experience really highlights why precision matters so much in data alignment. Even a tiny discrepancy can dramatically change what you're able to see, interpret, and ultimately understand from your data.
Mm-hmm.
It really underscores that simply getting a plot to appear isn't enough. It has to be a meaningful and ideally a complete plot.
Couldn't agree more.
So we've debugged the static image. We've got our 36 channels mapped. That's a huge win. We can now get a snapshot of brain activity.
Right, a snapshot.
But the brain, as we know, is anything but static, isn't it?
Definitely not.
It's a dynamic, ever-changing landscape of electrical activity. So how do we take this snapshot and turn it into a moving picture?
Mm-hmm.
What's the next big technical leap you had to tackle?
Yeah, that's the goal, right?
To move from a single moment to understanding how brain activity changes over time, especially related to specific tasks, like, say, imagining moving a hand. This leads us to event extraction and epicing, I assume.
Exactly. Event extraction and epicing. This step is absolutely vital for analyzing brain responses to specific events.
Okay.
Whether it's a simple flash of light, a sound, or in this particular case we looked at, a motor imagery task, thinking about moving your hand.
Right.
Our first attempt to extract events, these are specific timestamps in the data that mark when something significant happened.
Mm-hmm.
From the data's annotations, it yielded only one event, surprisingly labeled T0, just one.
T0. That sounds incomplete.
Right. And frustratingly, its corresponding epoch, that critical short segment of data around that event that we wanted to analyze, was immediately dropped. We got a no data error.
Oh no, after all that channel work.
Exactly. It was a real head scratcher. Like, what does T0 even mean here, and why is there no data around it?
So what did you do? Dig deeper?
We had to. That dropped epoch led us on a deeper dive into the raw.event files themselves. These were separate files alongside the main EEG data.
Okay.
We discovered they contained custom binary data, not just plain text.
Binary, ugh, never fun.
Tell me about it. And it also mentioned a time resolution that felt a bit unusual, 160 units per second or something like that. We tried interpreting the binary content, attempting to read segments as integers to maybe find event timings or codes. We even managed to interpret the last 8 bytes, which seemed to correspond to an event ID of 1, which actually matched the T0 we saw in the other annotations.
Ah, so T0 means ID1 progress.
Sort of. But here's the kicker. The time value we extracted for this T0 seemed really unusual. It didn't look like it was representing a typical, epochal event onset time.
Like the start of the hand movement thought.
Exactly. And that no data error we kept getting, it further screamed that this T0 in the .event file wasn't what we needed to segment our data effectively. It wasn't the marker for the task itself.
So you hit another wall. This is where it gets really interesting, though, right? Because it's a fantastic universal lesson for anyone working with data, not just brain signals.
Absolutely.
It's not just about crunching numbers or fixing code. It's about understanding the entire scientific experiment, the context, the why.
Precisely.
It's like being a detective solving a mystery by finally finding the missing manual. Without that fundamental understanding of what the T0 or maybe a T1 or T2 code actually means in the context of the experiment,
right,
all the technical skill in the world wouldn't let you interpret what was happening. It truly brings the science into data science.
Exactly. This pointed to a crucial insight. We couldn't just guess or infer the meaning of these codes. We needed to consult the official documentation.
The dreaded documentation.
Sometimes it's your best friend. In this case, for the EEG motor imagery dataset on the PhysioNet website. That's where you'd find the definitive details on the experimental protocol, the precise timing of stimuli, and the true meaning of those event codes. For instance, finding out that T1 likely meant left-hand imagery and T2 meant right-hand imagery.
Okay, and now, W, you can actually analyze the task.
Exactly. That moment when you realize the answer isn't hidden in your code, but in, like, a dusty PDF on a website. It's humbling, but also incredibly satisfying.
I can imagine. It's the core of what makes data science science.
Totally.
Okay, so after all that intricate detective work, the painstaking alignment, the deep dive into event timing, finally it's time for the payoff.
Yes, the fun part.
We've tackled the static images, we've grappled with the elusive event data. Now, how do we bring it all to life by visualizing the temporal evolution of EEG data through animation?
Yeah.
This is where we actually get to see the brain doing its thing. This sounds amazing.
This was the exciting goal, the grand finale of our data journey, to create a truly dynamic view, seeing the brain's electricity flow across the scalp like a digital dance.
The digital dance of the mind, I love it.
Our plan was simple in concept, but, required precision in execution.
Always the way.
Select a raw data segment, say, the first 5 seconds from our S01R02 file. Then, the trick was to generate a whole series of topomap plots for small, successive time intervals within that window.
Okay, like frames in a movie.
Exactly. Think of it like creating a flipbook, where each page is a tiny snapshot of brain activity at a slightly different millisecond.
Cool.
Finally, the magic happens by combining all those individual plots into an animated GIF using a standard image processing library like Imagio.
Okay, so loop through time, make a plot for each tiny step, stitch them together. Sounds straightforward enough, but I bet there were some last-minute coding hurdles, weren't there?
Oh, you know it.
The nitty-gritty that makes it all work, that often surprises you right before the finish line, because that's the reality of working with complex data.
Yeah.
It's rarely a straight line.
Oh, absolutely. You think you're there, you've climbed the mountain, and then the code throws a couple more curveballs just for fun.
Yep.
I vividly remember hitting a particularly frustrating type error related to unpacking the plot figure. It was like the plotting function was just shrugging its shoulders saying, I don't know what to do with this input.
Classic.
And then came a value error about invalid time ranges in the plotting loop itself, basically telling us, hey, you can't ask for a brain map that's 0 seconds long, which... Fair enough.
Right. You got to give it some time to plot.
Exactly. It's those little moments of despair followed by the aha when you realize the subtle misstep that truly define working with complex data.
Definitely.
But after some meticulous adjustments to how the plots were generated and how those tiny time windows were defined, we celebrated a triumph. 50 top map frames successfully generated.
Nice. 50 frames.
Each frame a tiny, perfect piece of the brain's dynamic story over those first 5 seconds.
And the result is this dynamic animation that shows how brain activity actually changes over time, which is so incredibly powerful for understanding what the brain is doing during tasks like motor imagery.
It really is.
Imagine how cool and genuinely fun it is to watch those electrical signals ripple and shift across the scalp in what feels like real time. It's like that digital dance of the mind you mentioned. We can even save this captivating animation as a GIF, right? And maybe adjust its display size if needed to make sure it looks absolutely perfect on screen.
Yep, save it as a GIF, share it, analyze it. That's truly seeing your brain in action.
What an incredible journey we've taken today, seriously. From wrestling with mismatched channel names and deciphering mysterious binary event files, all the way to creating a living, breathing animation of brain activity. It truly highlights the fascinating blend of technical skill, relentless problem solving, and sheer scientific curiosity required in this field.
It really does.
It's a powerful reminder that data is never just numbers. It's a story waiting to be told if you're willing to do the detective work.
Well said. And this deep dive into EEG data visualization really highlights that the human brain isn't just a static collection of regions like you see in some textbook diagrams.
Right.
It's a constantly shifting, dynamic landscape of electrical activity. What's fascinating here, I think, is thinking about how seeing this dynamism, this digital dance, could open entirely new doors.
Like what kind of doors?
Well, whether it's understanding neurological conditions like epilepsy better by observing how seizures actually propagate across the brain, or designing more intuitive brain-computer interfaces that could help people control devices just with their thoughts.
The BCI stuff is amazing.
Or maybe just deepening our appreciation for the incredible complexity happening inside our heads right now, every single second. It's quite something.
It really is. And for you, our listener, think about how these visualizations aren't just cool to look at, right? They could potentially help us not just understand the brain in general, but maybe even personalize interventions or training based on an individual's unique brain activity patterns.
That's a really exciting frontier.
Imagine optimizing learning or even rehabilitation after injury by actually seeing how a specific brain responds to different approaches.
The possibilities are huge.
Definitely something for you to mull over until our next deep dive. Keep those neural networks firing.
So we're doing reviews. Obviously, this is Notebook at Lamb. Go check it out. I don't think it needs advertising. Okay, so we do have a human in the loop. Just if you were wondering, we are developing this website. That's the main reason we are here. And eventually, if anything interesting comes up of this, which is already is, so it's probably going to eventually go on to bionichaos.com. So, yeah. So if you have any more specific questions, especially after visiting the site, I'll be more than happy answering those.
Everything we do is available freely on bionichaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Yeah, and you just have to do whatever the AI lady said.